Well, happy Wednesday. Hope everybody's doing well, getting ready for the holidays. We are going to dive right into flowcharts tonight. And then after flowcharts, as I mentioned on Monday, we'll take a look at, I want to go over, just pull up the schematic. There's a page of schematic symbols, just so you guys are aware of where that is located. You need to review those. You'll get some questions about schematic symbols on the TKT. And then we're going to take a look at a little bit of the assessment in terms of the practice assessments. And we'll use that as an opportunity to do a little bit of review as we go through the assessment, some of that as a group. All right, so let's dive right into flowcharts. You guys see my screen?
It says flowcharts. Yeah, it switched.
Beautiful, beautiful. All right, so talking about flowcharts, first thing we're going to try to accomplish in this session is look at the purpose, why we have flowcharts, why we use flowcharts. Look at some of the symbols, basically the shapes. What do the shapes mean, and how does that help us as we utilize this flowchart? Flowchart, first of all, it's, what is it? Well, it's a graphical representation of a process. I think today you see flowcharts typically, if you've got things that you purchase and you need to assemble, a lot of times they will have flowcharts with them. Do this, then this, then this, and then you got if-then statements. But we can see in terms of in the beginning, flowcharts were very helpful in computer science because in terms of programming, it was a way to graphically, visually capture what you're trying to accomplish. And so you could have, all the different components that you had to account for, especially those that if one existed, you need to do one thing. If the other existed, you need to do something else. And so this flowchart will kind of create this map of walking toward a destination or to some accomplished goal. You can also use it a lot. You'll see it in troubleshooting, also aid in reasoning. Once again, anytime that you've got to logically walk through some process, a flowchart is a pretty good way to do it. We're going to take a look at some of the common flowchart symbols. They're pretty simple, especially the early ones that we're going to look at are really simple. But then there are some that are more unique, some that you may have never seen before and possibly will not see again. Some are a little bit more obscure. If we take a look at this Terminator symbol, this oval shape, usually your flowchart is going to have a start and a stop. It's going to have a place where indicates, this is the beginning, and then stop, meaning that you are done. Obviously, those are pretty self-explanatory in terms of what should happen on each one of those. But it's important to have a start and a stop. Sometimes I think when we write out, instructions, or we take for granted that a lot of people would wind up at the same place we would, without indicating, okay, where you should start and where you should stop. And so these are key. Usually you'll have them there. It's nothing more than a reference point in terms of a start and a stop. This rectangle process symbol. And so it's something is going to happen. There's going to be something that's processed there. Something is changed in some way. You can see here, this is saying add 10, 11 greater than 12. We're processing whatever information we have at this point. We're changing what is taking place and what data we have to this point. And so this process symbol could be anything that you're going to actually process there, anything that you're going to do, but typically we'll put that. And the nice thing about putting that in a rectangle is that we immediately recognize, okay, something's going to take place here, right? Very different than the start. The start, okay, identifies the location. This identifies that we're actually going to do something. This diamond, the decision symbol, you know, we're basically making a decision on which path to continue on. You know, here it says greater than 10, yes or no. So you're taking a look at the data and you're making a decision on which path to continue. You know, true, false. You know, if you think about some of the logic that we talked about, you know, that binary logic, here we have, once again, you know, either or, a yes or a no. You know, it's a true, false. It's one way or the other. Right here, we're thinking through the logic piece of it. So we're not necessarily building those gates at this point, but it allows us to capture. If I start and I change my data, I process it somehow. Okay, is the outcome, does it call for me to continue on in one direction or the other? So anytime I see this diamond, you know, I'm going to make a decision about the direction that I'm continuing to move. This circle is a what they call on-page connector. On-page meaning that if I'm looking at my flow chart, that connector should be on the same page that I'm looking at. Right, this circle, I should be able to see this circle somewhere so that I know that those 2 points are connected. You know, sometimes if you look at the process, it could be so complicated that I can completely fill up a page, and it's easier to draw these connectors just as a circle versus it becomes simpler than trying to connect via all these lines, right? And so what we're doing here is we're just using this as a on-page connector. You know, look somewhere else on the page, and you're going to see, you know, this other A, right? You have these two A's, and well, those two A's are connected. They are the same point, if you will. You know, very different than the stop. You know, we had the oval where we had a start or a stop. You know, once I get to A, I see this. That doesn't mean I'm done. It just means that the rest of the flow chart is connected somewhere else, and it's on that page. Now, if we see something that looks like a home plate on on a baseball field, something that looks like this. Now, this is also a connector, but this is a off-page connector, meaning that it's on a different page. You have a A1. Well, I'm going to have a corresponding A1 on a different page. You know, this would be for a large flow chart that requires multiple pages. You know, very complex process. And so I'm going to look for an off-page connection. You know, simple arrow, all that's indicating is, you know, direction. As we're progressing through the flow chart, we want to make sure that we're moving in the right direction. That's usually pretty clear from our start stop. But if you get to some of the decisions and multiple paths to take, you know, it's possible that, you know, you could get confused, and so therefore these arrows indicate the direction that you're moving in the flow chart. Couple other flowchart symbols, and like I said, these are some of the more obscure flowchart symbols, the ones that you you probably haven't seen and may see or may not see. We've got a document symbol. This is used to represent a document or report in a process flow. So maybe there's a a spreadsheet that is connected with this, or a document. We've got this that they call a rectangle with a top that slopes from left to right. A manual input signal, a symbol. So here, this indicates that we have something that we have to do, something that we're going to manually input into this flow chart. So this could be, we're walking through the flow chart, and then there's something that I have to collect, and it's not automated. It's something that manually I have to go in and pull that information into the process. This rhombus is an input-output symbol. So we're either inputting or outputting data. Typically, if we're going to, review the data, we're going to show it maybe on a monitor, or it could be even, output of, we're going to print it out. We're going to see something that looks like this input-output rhombus. Predefined process symbol shows the name of process subroutine, which is defined elsewhere. So this could be a process that's already laid out step by step, and so we would see this rectangle with these two defined lines, and we would know, okay, now we need to go to the subroutine that we've laid out somewhere else in the entire process. Internal storage. So we're going to store whatever we have at this point. Here's a sample of a flow chart and what it might look like if we were working through a flow chart. This is an example of troubleshooting a lamp. This is extremely simple, and even you can see that really doesn't have a start stop, right? But it has some of the elements that we've talked about. It's pretty clear that we're going to start at the top. Typically, when flow charts are laid out, they usually will start either top or left and work bottom or right. So here we see that we're actually top left. Lamp doesn't work. We come to a decision. Is lamp plugged in? We've got a yes or no. This is pretty easy to step through, but you can see how I'm making a decision, and if it's yes, if it's plugged in, then I'll continue to move down the pathway of yes. This bulb burned out? Yes or no? And each time it's telling me what action I should take as I get outside of these decisions. If the lamp's not plugged in, I would follow this path. We'll plug the lamp in. It makes perfect sense. Lamp is already plugged in. There's no reason to worry about that. It's already plugged in, and so I go the yes path. Well, maybe it's the bulb that's burnt out. And so, is the bulb burn out? Yes or no? Now, obviously, this may require some testing, or it may require a small removal of the bulb and visually inspect the bulb, or measure the bulb, or the soft gentle shake of the bulb. But somehow we have to determine, is this bulb burned out or not? If it's yes, then replace the bulb. If it's no, then we've got something else wrong with the lamp. This flow chart is not meant to really capture every possibility of what could be wrong with this lamp. It's really just meant to show us an example of a flow chart and how we could step through the troubleshooting process. And you can see, if you've got common equipment, and if the equipment has typically, as most equipment does, some common failures, when you troubleshoot, if you will document what you troubleshoot and what the problem is and what the what the fix was, eventually you can collect enough information where you can build a flow chart for someone who has much less experience troubleshooting whatever that item may be, and they would be able to step through the troubleshooting process and get to a solution fairly quickly without having to build all the months, years of experience that it may have taken to capture everything that could go wrong with whatever device it may have been. And so a lot of times, when you're working with equipment and you're seeing in a manual, it's not uncommon to have these flow charts in the back of a troubleshooting section so that you can walk through steps. Now it may be much more complicated than is a lamp plugged in. Maybe measuring test points and validating voltages and other things of that nature, but the process is still the same. As you're walking through the flow chart, you're getting to rule out some things and walk toward a solution that will be the overall fix of whatever the equipment failure may have been. Here's another example of a flow chart. Now we've got the flow chart itself, and then we got the calculations over here so we can see exactly what's taking place. Basically, we're calculating a profit or a loss. We're going to start at our start oval. Makes sense. We've got our rhombus here where we're going to input some information. Read income. Income was 1,000. We're going to read cost. Cost was 800. Is income greater than cost? Well, 1,000 is greater than 100. So yes. Calculate profit as income minus cost. So 1,000 minus 800, which would be 200. Print profit. So we print it out and we have our 200 profit. Now, if for some reason those were reversed, let's say that cost was greater than income, when we got to this decision symbol, income greater than cost, it would have been no. And so we would have moved down to calculate loss. If those two values are reversed, then let's say it was a cost of 1,000 and income of 800, then we would print 200 loss. You can see this is basically nothing more than our flow chart, once again stepping us to the logical conclusion. And the great thing about having a flow chart like this is once you have the process perfected, then you can just plug in the numbers or plug in the decisions or plug in the data where you need to, where it's called for, and we will get the correct output, correct ending figure. Now this is an example of a much more, some more complicated flow chart. In fact, this is a flow chart that would be a little bit challenging to follow. Laptop internet connectivity. Do you see a wireless network? We'll just start at the top. Do you see a wireless network? No. We'll switch on enabled. Is it on? No. Well, don't be embarrassed. The switch can be turned off in normal handling. Switch enabled, yes. The router active in range? No or yes. Is it your home network? No or yes. And so you can continue to step through this, right? And this will lead us to the appropriate decisions and the appropriate actions to ensure that we have laptop internet connectivity. You can see that this looks like it could get, looks like it's complicated, but it's really, just making a yes or no decision and then moving in the appropriate way. Just like if, this is not the goal for these flow charts. I don't want you to think that what I'm about to say, you should be able to do this, but this is just like when we were looking at gates and we're looking at digital logic. And remember those gates, and gates or gates, or when we start putting those gates together, we can do the same thing. We can create electronically this circuit that will give us, that represents what this flow chart also represents. Some of that same logic. We can have a gate and cause a series of inputs to give us the appropriate output. Here, it's just a matter of us making decisions, yes or no decisions, as we step through toward a solution. You can see as we work from top to bottom, typically when we get down to the bottom, we should be at a point where we have some solution, or we have indicated that it might be something that's outside of our control and we need to take a major step. This is another flow chart that this looks like it's for a patient, for a doctor's office. You start at the top, patient arrives, is the patient registered? Yes or no. No will register the patient. It goes back, is the patient registered? Yes. And this is a common little feedback loop that often, if there's something that has to be done before you can move to the next stage, then you'll see this yes, no, and no will take the action. And then if you've taken that action, it goes right back to that same decision tree. And this is where it becomes important to make sure that these arrows, that we're following these arrows, because if we get register patient, yes, no, well, wait a minute, what's this? And make sure you're following the arrows. This is a little feedback loop here. It's always going to go out, no, back to registered patient. If we've done this process, our answer is going to be different. So yes, and then it's going to be, okay, available nurse. If there's a nurse available, then we're going to move to the next step. No nurse available, we're going to wait. And we're going to wait here. Usually the wait for the nurse is nowhere near as long as the wait for the doctor. But this is usually about maybe 10 minutes. This is usually about 2 hours. So we're going to spend some time in that loop. But you can see we're just stepping through this. Yes, record health condition. Is there a doctor available? All four corners of this decision box has a line either going out or two going in, two going out, right? So we got to get to this point. Is a doctor available? Yes. Okay. Assign the patient to doctor. Doctor not available. Okay. Wait for doctor. And then we get in this loop. Doctor available? Nope. Nope. And then eventually doctor's available. We assign the doctor to the patient, or assign the patient to the doctor, and we continue on. So this is a good example of these little feedback loops, just to make sure that we're moving in the right direction. You can see this is not something that is extremely hard. However, it could be very valuable because even if, something as simple as, well, how do we design our, the layout of our, our medical office? Well, okay, let's talk about this process. What flow do they need to go through? Well, they need to hit somebody to register first, and then we're going to see nurses, and so we need to be able to set up our physical office so that this flow makes some sense when we look at our office. You know, you don't want patients that, okay, we're going to push back to the area where the doctors are, and then we'll have them come back up front to be registered, and then push back to, you know, a holding area, and then brought back to an available nursing station. You know, it needs to make some sense. And so this chart, you know, being able to, you know, visually capture what's going to take place, you know, it certainly lays out the process, but it could have other benefits as well when we're making other decisions about things that should be connected to this process. So as you can see, flow charts are, I mean, they're not very difficult at all. You know, they're pretty straightforward. I think the basic questions that you may see about flow charts is going to be about what the purpose of a flow chart would be, you know, visually capture that process. And then you may see some of those basic symbols, but that's going to be pretty much it. Let's take a look at, I don't remember who it was, but somebody requested on Monday, being last day of class, we watch a bunch of videos. So we won't watch a bunch, but I will show you this one.
I'm guessing there's no sound to this. Okay, just making sure.
Yeah, there's no sound. All right, so let's go. All right, so hopefully you guys can see my screen. Let's take a look at schematic symbols. You guys see that page?
Yes.
Cool. All right, so one of the things that I've heard in the past is that a lot of times there are questions about schematic symbols, and you've got a sheet, this sheet, that lists schematic symbols. I would take a look at that. Many of these we have talked about, resistor, earth ground, a cell, battery, chassis ground. I'd make sure that earth ground versus chassis ground. Those seem to pop up on a regular basis. This variable resistor. I don't know necessarily that I've had anybody say in the past that, oh, I was asked a question about the schematic of variable resistor, but even if you are, just remember this wiper on this resistor we talked about in terms of, a rheostat or a potentiometer, a diode. That diode is the device that only allows electrons to flow in one direction, not the other direction. And so we used it for rectification. Zener diode, looks like we got this Z here. This, once again, you can tell it's a diode. See these little arrows coming off of it, so it's a light emitting diode or a LED. We had our transistors. Remember, the way we tell the difference between a NPN and a PNP, it's all about this triangle. This triangle will always point to the N type material. It's always on the emitter, right? And so this emitter is pointing out. So this emitter is N type material, so NPN. Here we can see the emitter is up on the top. It's pointing in toward the base, and so that means the emitter is positive. So it's PNP. So we can tell the difference between those types of transistors. We had a capacitor. The difference between this capacitor and the electrolytic capacitor is the polarity. You can see we get this curve on the negative side, straight on the positive side. This electrolytic capacitor can't be put in either way. It's got to be in the correct orientation, where this capacitor doesn't matter. Inductor, remember that was that coil of wire that opposes the change in current flow. And then we use that field effect, that magnetic field that builds up around this coil whenever we get current in the wire. We put that next to another coil, and we call that a transformer. Okay, so let's go back and look at the other side. Our gates, AND gates and OR gates. The XOR, this buffer. And then we started putting our bubble inverter on these. So it turned it into instead of an AND, a NAND, instead of an OR, a NOR, or an XNOR, a NOT gate. Whatever comes in, it's going to be the opposite going out. Then we had our flip-flops. Right? So this was you see the input up here of a D. So this was our D or a D latch flip-flop. This is our R and S. So this is our RS flip-flop. And then our J and K. So this is a JK flip-flop. Makes it real easy. A symbol for resistance, ohms. So this was our symbol for a Schmidt trigger. Remember, that was the device that was going to take an input wave and going to really make it a square wave. We talked about the iron core transformer. You could see something, you know, this relay. We didn't necessarily talk about relays. Let me show you something on relays, but basically think about what we already know in terms of this is a coil. This was an iron core. Well, as we get current in this coil, knowing what we already know about inductors and transformers, what's going to happen when we get current in this coil? Remember we said that in an inductor, when we've got current that's moving through that coil, we get that magnetic field that builds up around the coil. And when we've got this iron core, that magnetic field is going to be transferred even better. And so what's going to happen is this wiper is going to change contacts based on whether that we have this magnetic field or not. If we've got current flowing, this magnetic field is going to pull the wiper to this contact. And so now we've got, you know, this portion of the circuit connected. No current flow, you know, spring loaded. So this magnetic field is going to spring back. And now I've got, you know, these 2 points connected. Let me show you something about relays, but just know that that's what that is. That's a relay. You know, very common. So I would go back and, you know, review the schematic symbols. Definitely make sure that you know the major schematic symbols that we talked about. And then I would also, you know, one that seems to pop up all the time is earth ground or chassis ground. Being able to tell the difference between those 2 symbols, making sure that you know what is earth ground and what is chassis ground. All right, so hold on while I'm thinking about it. Let me check relays right quick. Okay, so let's take a look at this information on relays. Won't take much time.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at relays to understand the main parts, the different types, as well as how they work. For all of your relay needs, check out Telecontrols, who have kindly sponsored this video. Telecontrols are one of the leading manufacturers in the automation industry since 1963. They offer some of the best solutions when it comes to reliable switching relays, and they guarantee the maximum lifespan for your equipment. Check out their switching relay portfolio along with suitable relay bases and accessories. You can contact them via email at sales@telecontrols.com or through LinkedIn to receive your free relay configuration cheat sheet. For more information, see the link in the video description down below. A relay is an electrically operated switch. Traditionally, relays use an electromagnet to mechanically operate the switch. However, newer versions will use electronics, such as solid-state relays. Relays are used where it is necessary to control a circuit using a low power signal, or where several circuits must be controlled by one signal. Relays ensure complete electrical isolation between the controlling and the controlled circuits. Relays are often used in circuits to reduce the current that flows through the primary control switch. A relatively low amperage switch, timer, or sensor can be used to turn a much higher capacity load on and off. We'll see examples of this a little later in the video. There are two main circuits in the relay, the primary side and the secondary side. The primary circuit provides the control signal to operate the relay. This could be controlled by a manual switch, a thermostat, or some other type of sensor. The primary circuit is generally connected to a low voltage DC supply. The secondary circuit is the circuit which contains the load which needs to be switched and controlled. When we talk about a load, we mean any device that will consume electricity, such as a fan, a pump, a compressor, or even a light bulb. On the primary side, we find an electromagnetic coil. This is a coil of wire which generates a magnetic field when current passes through it. When electricity passes through a wire, it creates an electromagnetic field. We can see that by placing compasses around the wire. When we pass a current through the wire, the compasses change direction to align with the electromagnetic field. When we wrap the wire into a coil, the magnetic field of each wire combines together to form a larger, stronger magnetic field. We can control this magnetic field by simply controlling the current. By the way, we have covered how solenoid coils work and even how to make your own solenoid in our previous videos. Do check that out, links can be found in the video description down below. At the end of the electromagnet, we find the armature. This is a small component which is pivoted. When the electromagnet energizes, it attracts the armature. When the electromagnet is de-energized, the armature returns to its original position. Typically, a small spring is used to achieve this. Connected to the armature is a movable contactor. When the armature is attracted to the electromagnet, it closes and completes the circuit on the secondary side. We have two types of basic relay, the normally open and the normally closed type. There are other types of relays, and we're going to look at these a little later in the video. With the normally open type, no electricity flows in the secondary circuit. The load is therefore off. However, when a current is passed through the primary circuit, a magnetic field is induced in the electromagnet. This magnetic field attracts the armature and pulls the movable contactor until it touches the terminals of the secondary circuit. This completes the circuit and provides electricity to the load. With the normally closed type, the secondary circuit is normally complete, and so the load is on. When the current is passed through the primary circuit, the electromagnetic field causes the armature to push away, which disconnects the contactor and breaks the circuit. This cuts the supply of electricity to the load. The operation of solid-state relays, or SSRs, is similar in principle, but unlike electromechanical relays, it has no moving parts. The solid-state relay uses the electrical and optical properties of solid-state semiconductors to perform its input and output isolation as well as switching functions. With this type of device, we find an LED light on the primary side instead of an electromagnet. The LED provides optical coupling by shining a beam of light across a gap and into the receiver of an adjacent photosensitive transistor. We control the operation of this type of relay by simply turning the LED on and off. The phototransistor acts something like an insulator and doesn't allow current to flow unless it's exposed to light. Inside the phototransistor, we have different layers of semiconductor materials. There are N-type and P-type, which are sandwiched together. The N-type and P-type are both made from silicon, but they have each been mixed with other materials to change their electrical properties. The N-type has been mixed with a material that gives it lots of extra as well as unneeded electrons. These are free to move around to other atoms. The P-type has been mixed with a different material, that has fewer electrons. So this side has lots of empty space where electrons can move to. When the materials are joined together, an electrical barrier develops and prevents the electrons from flowing. However, when the LED is turned on, it will emit another particle known as a photon. The photon hits the p-type material and knocks the electrons, pushing them across the barrier and into the n-type material. The electrons of the first barrier will now be able to also make the jump, and so a current is developed. Once the LED is turned off, the photons stop knocking the electrons across the barrier, and so the current in the secondary side stops. So we can control the secondary circuit just by using a beam of light. There are many types of relays, and we're going to now consider a few of the main ones, as well as some simple examples of how they are used. Let me know in the comments section how and where you've seen relays used. Or even better, tell me what ideas you have for their application or any project you're working on where they could be applied. As we have seen earlier in this video, we have the simple normally open relay. This means the load of the secondary side is off until the circuit is complete on the primary. We could use this, for example, to control a fan by using a bimetallic strip as a switch on the primary side. The bimetallic strip will bend as it increases in temperature. At a certain temperature, it will complete the circuit and turn the fan on to provide some cooling. We also find normally closed relays. This means the load on the secondary side is normally on. We could, for example, control a simple pump system to maintain a certain water level in the storage tank. When the water level is low, the pump is on. But once it reaches the limit we require, it completes the primary circuit and pulls the contactor away, which cuts the power to the pump. In a standard normally open relay, once the primary circuit is de-energized, the electromagnetic field disappears and the spring pulls the contactor back to its original position. But sometimes we want the secondary circuit to remain live after the primary circuit is reopened. For that, we can use a latching relay. For example, when we press the call button on an elevator, we want the light on the button to remain on, so that the user knows the elevator is coming. So we can use latching relays to do this. There are many different designs for this type of relay, but in this very simplified example, we had 3 separated circuits and a piston which sits between them. The first circuit is the call button, the second is the lamp, and the third is the reset circuit. When the call button is pressed, it completes the circuit and powers the electromagnet. This pulls the piston and completes the circuit to turn the lamp on. A signal is also sent to the elevator controller to send the elevator down. The button is released. This cuts the power to the initial circuit, but as the piston isn't spring-loaded, it stays in position.
He works in Manville, I work in Conroe.
Somebody need mute the phone.
And we live
Hey,
right
hold
here.
up.
Building
Nope.
agency.
The lamp remains on. Once the elevator car reaches the lower floor, it makes contact with the off switch. This powers the second electromagnet and pulls the piston away, cutting the power to the lamp. Latching relays therefore have the benefit of having positional memory. Once activated, they will remain in their last position without the need for any further input or current. Relays can have single or double poles. The term pole refers to the number of contacts switched when the relay is energized. This allows more than one secondary circuit to be energized from a primary circuit. We could, for example, use a double pole relay to control a cooling fan as well as a warning light. Both the fan and the lamp are normally off, but when the bimetallic strip on the primary circuit gets too hot, it bends to complete the circuit. This creates the electromagnetic field and closes both contactors on the secondary side. This provides power to the cooling fan as well as the warning light. When dealing with relays, you'll often hear the term throws. This refers to the number of contacts or connection points. A double throw relay combines a normally open and a normally closed circuit. A double throw relay is also called a changeover relay, as it alternates or changes between two secondary circuits. In this example, when the primary circuit is open, the spring on the secondary side pulls the contactor to terminal B, powering the lamp. The fan remains off because the circuit is not complete. When the primary side is energized, the electromagnet pulls the contactor to terminal A and diverts electricity, this time powering the fan and turning the lamp off. So, we can use this type of relay to control different circuits depending on an event. A double pole double throw relay, or DPDT, is used to control two states on two separate circuits. Here we can see a DP-DT relay. When the primary circuit is not complete, terminals T1 and T2 are connected to terminals B and D respectively. The red LED and the indicator light are energized. When the primary circuit is closed, then T1 and T2 connect to terminals A and C. The fan turns on and the green LED is also energized. Something we need to consider when working with electromagnets is the back EMF, or electromotive force. When we power the coil, the electromagnetic field builds up to a maximum point. The magnetic field is storing energy. When we cut the power, the electromagnetic field collapses, and this releases the stored energy very quickly. This collapsing field continues to push the electrons, and this is why we get the back EMF. This is not a good thing, because it can produce very large voltage spikes which damage our circuit. To overcome this, we can use something like a diode to suppress this. The diode only allows current to flow in one direction, so in normal operation, the current flows to the coil. But when we cut the power, the back EMF is going to push the electrons, and so the diode will now provide a path for the coil to dissipate its energy safely, so that it doesn't damage our circuit. Okay, that's it for this video.
Okay, so you saw a bunch of different relays. I guarantee you will not be asked that much information about relays, but at least whenever you see that schematic, you know that that's going to be a relay, and you have a little bit more of an understanding of the operation of a relay and the switching that takes place with using that control side and the usually larger side. All right, so let's see. All right, you guys see my presentation? Let's do this. You see the question?
Yeah.
All right, so let's just step through this, and we'll talk through some of these. This is a different. Now, I'm not gonna say that they won't have some questions that are the same. We'll see if there's some questions that you've seen before on the other assessment that's in the course. But this is a different set of questions, and then I'll put these in the course so that you'll have these as well to go through and review as you continue your studies. But let's just walk through some of these and talk through these and see if there's some areas that we need to go back and take a look at. So the rate of electron flow in a circuit is expressed in units called what?
E.
Okay, so B, is that what I heard?
Yeah. Ampere.
So amperes, right? So amperes, we're talking about rate of electron flow. So that's current. And so, yeah, we're looking at amperes. Very good. A resistor of 26 ohms is connected in parallel with another resistor of 26 ohms. In series with this combination is a 57 ohm resistor. The 70 volts is applied to this complex connection. The voltage drop across the 57 ohm resistor would be what?
C. 70.
70 volts. All right, so just looking at this, we've got 70 volts applied, right? And so we're not going to drop all of it across that 57 ohm resistor.
A, 13.
Okay, 13. And how did you come up with
I say
13?
A.
You say A as well?
Yeah, because I lost track of what I'm looking at here, but I remember you saying something about if you have two resistors of the same number, you get less than half or something like that. Am I thinking of it wrong?
No, you're right. You're right. And so, what I hear you guys saying is, the first step is we got to figure out, what our total resistance is. And so when we look at those two resistors that are in parallel, R2 and R3, they're both 26 ohms. And so we know we could redraw that circuit as one 13 ohm resistor. One of those shortcuts we had was the value of the resistor divided by the number. So two 26 ohm resistors. So we get 13 ohms there. And so then the question is, if I redraw this circuit with a 57 ohm resistor and a 13 ohm resistor, then what is my total current? Actually, instead of taking two steps, let me take one step. If I redraw this circuit as a 57 ohm resistor in series with a 13 ohm resistor, what's the total resistance? Let me ask that question.
Total resistance is 70 ohm.
70 ohms. Okay, so if total resistance is 70 ohms, then what is my total current?
1.
Remember, using Ohm's law, we're going to take our total voltage divided by our total current, 70 volts divided by 70 ohms. So 1 amp, right?
No, it's
So
57.
So now if it's 1 amp, it's going to be flowing in this circuit, and it's going to flow, 1 amp is going to leave the negative side of the battery. It's going to, half amp and a half amp, and then it's going to come back together. So we're going to have 1 amp through R1 if we use Ohm's law. And you're right, 57 ohms is going to be, or 57 volts is going to be the answer, right? Everybody see how we got to 57 ohm or 57 volts for the voltage across R1? Any questions about that? Okay.
Recording in progress.
What was that question? Okay, so you can see right here, we've stepped through it. Our equivalent resistance, we came up with 13 ohms. That's these two in parallel. 26 divided by 2, we got our 13 ohms. We put it in series with our 57 ohms to get a total of 70 ohms resistance. We used Ohm's law to get our 1 amp total current and work toward our 57 volts across R1. All right. How do we convert 65,000 ohms to kilo ohms?
That's C. That's 6.K.
Okay. How did we know how many places to move? How did we get 6.5?
Kilo ohms is you move it over 3 spaces.
Yeah, so kilo ohms is times 10 to the third. And so we decided that we'd move it 3 places. Remember, if you
It's
get
like
confused,
a dollar.
yes, yes. Remember, if you get confused about which way to move it, we've gone up in terms of our unit. And so our number is going to look smaller. You know, here we had no unit, but our 65,000. You know, these are basically the same, right? This is 1,000, 6.5 kilo or 1,000. So yes, we moved it 3 places, 6.5 kilo. Perfect. About 33 milliamps. We're going to convert that to amps.
I can't remember this one, but I'm going to say A.
You'll say A, okay?
Yeah, I'm gonna say A2.
So, you know, keep in mind, milli is times 10 to the negative third, right? And so the thing that we can say is just, you know, this is smaller, milli times 10 to the negative third versus nothing here, right? So our unit is getting larger, if you will. This was milliamps. This is just amps. So our unit's larger. If the unit's larger, then the number is going to be smaller. Right here, we had 33 milliamps. Well, if I'm going to move this 3 places, I can't move it 3 places to the right and be 33,000. And so it's going to be 3 places to the left, 0.033 amps, right? So once again, you know, the real secret to these questions is just knowing the value of this prefix. Kilo times 10 to the third, milli times 10 to the negative third. And then it's just a matter of moving your decimal. In an RCL circuit, the phase difference between voltage and current is blank. Right? So a resistive RCL means resistive, capacitive, inductive. So RCL circuit, we've got all 3 of those. And, you know, we talked about the phase relationship, you know, in a inductive circuit, Eli, voltage led current by 90 degrees. And then we had in a capacitive circuit, we said ice, which meant that current led voltage by 90 degrees. So what do you think if we have an RCL circuit? How do you think these two, voltage and current, what do you think the relationship is between the two? So let's just look at the explanation. Less than 90 degrees, when you combine a reactive component with a resistor, the phase difference will always be somewhere between 0 and 90, right? And so, you know, if we're talking about a purely inductive and capacitive, then our voltage and current would be completely out of phase. But since we're talking about a resistive, capacitive, inductive, it's going to be less than 90 degrees. I have not had anyone come back and say that they had to do any calculations on RCL circuits. You know, I'd be aware of Eli the Iceman, just in case they ask you the phase relationship in an inductive or a capacitive circuit. But outside of that, I think you'll be fine. Electrical doorbell has a resistance of 70 ohms and requires a current of 2 amps. The voltage necessary to operate the bell. All right, so we're going to use Ohm's law and calculate the voltage. Voltage is equal to current times resistance. What's our answer going to be here?
You would do a 70, no, 2 divided by 70? No, 70 divided by 2? Is that what you're saying?
Yes, so the voltage is equal to current times resistance. We're given our current of 2 amps and we're given our resistance of 70. And so the question is, once we do the math, then how do we convert it to the answer that we have below, right? The Ohm's law portion, 2 times 70 is going to give us 140 volts, but all the answers are given to us in kilovolts. So what do you think? What was it?
It's a 1.4.
1.4.
140 volts, right? We take 70, multiply that by 2, we get 140 volts. And so now how do we represent 140 volts in kilovolts?
1.14.
0.14. Yep, 0.14. Now, remember, as we talked when we were dealing with numbers early on, we don't like this. This is typically not the way we would represent this voltage. We would much rather say 140 volts versus 0.14 kilovolts. So this, I'm not a big fan of this answer, just because this is not the way we would typically represent that number. But in terms of the options given, yeah, that's the most correct, 0.14. We had 140, and then to make that kilo, we had to move it 3 places. So 1, 2, 3 gives us 0.14 kilovolts. All right, now series DC circuit containing only resistance. If another resistor is added, the current will be increased, decreased, A or B, depending on the value of the resistor, or unchanged.
C.
C?
Yeah, they can be increased or decreased.
Okay. So we're asking if in a series DC circuit containing only resistance, if another resistor is added, the current. So we're asking the impact on the current.
So the reason C, the add is series or parallel. How they add that resistor?
So it depends on the configuration. The only thing is, it did say in a series DC circuit. So does that make a difference?
Then there will be increase if it's only add on series.
So if we have a series DC circuit and we add another resistor to that circuit, our current is going to, let's put some values to it. Let's say I've got a 1K ohm resistor. That's the only resistor I've got in this series circuit. And then I add another 1K ohm resistor. So now I've got two 1K ohm resistors in series. What's going to happen to the current?
Decrease.
It's going to decrease, right?
Yeah. So,
yeah. It's got to decrease because I'm increasing resistance, and we know that our current and our resistance are inversely proportional. And so as I add more resistance, it's going to decrease my current, right? Now, to your point earlier, you mentioned, well, it depends on if it's in series or parallel. Certainly, if it was in parallel and we add another resistor, that's when that notion of it's always the total resistance is always going to be smaller than the smallest resistor. You know, we would add another resistor, which also adds another path for current to flow in parallel, which could increase current. But in series, I add resistance. The more resistance I add, the less current I'm going to get. All right, in a series DC circuit containing only resistance, so only resistance, if another resistor is added, the current will be series DC circuit containing only resistance. If another resistor is added, the current will be. I don't know about that question. Let's see if we've got 45 volts in the schematic. We've got R1 is 45 ohms, R2 is 45 ohms. What's our current going to be in this circuit?
Like D, 0.5 amp.
0.5 amps,
Yeah.
which is
500.
500 milliamps.
Yeah.
Right. Yep. Absolutely. And this is a much better example of how we want to represent these numbers. Instead of giving the number with a decimal starting, let's go ahead and move the decimal place. So instead of having 0.5 amps, let's move it 3 places to give me 0.5 or 500 milliamps. Very good. Voltage is a measure of quantity of electricity, velocity of electricity, electron flow in a conductor, electromotive force.
Force?
Force, exactly. When we're talking about voltage, remember it was that potential difference, that ability to move electrons, not necessarily the measure of the movement, but if we've got that voltage difference, that's what's going to cause those electrons to flow, right? And so it's the electromotive force. It's the difference when we're talking about a river. The difference in elevation. If there's no difference in elevation, that river is not going to flow. If there's great distance, great changes in elevation, there's going to be a lot of flow. And so it's that electromotive force that's going to push those electrons negative to positive. 200 microfarads is the same as, once again, this is a question where you start thinking about the unit, microfarads and farads. Okay, that's capacitors, and it's easier if you're not careful. It's easy to get a little bit confused. But the real question is, if I convert 200 micro to standard units, what is it, right? And which one of those numbers might be correct?
I'm gonna guess A.
Gonna guess A. So keep in mind, micro is 10 to the what?
6.
The -6, right? 10 to the -6. So that means we're going to have to move this, this decimal to get to just farads. We'd have to move this decimal 6 places, right? So if I'm here, it's going to be 3. I'm going to move it 3 more, so that'd be 0.0002 farads. And so this is still too large. this is too large, 0.02 farads. And what they've done here, now keep in mind what this says, this looks a little confusing, but what they're saying here is 10 to the -4 or 10 to the -6. This is a power, right? This is supposed to be an exponent. So 2 times 10 to the -4 or 2 times 10 to the -6. If we started off with 200 micro, and we said that this was times 10 to the -6, that just doesn't make any sense to move the decimal and we still be 10 to the -6. I mean, that's basically saying that 200 microfarads is equal to 2 microfarads. And so the only answer that could make any sense is B. And you can see what they've done is they took 200 times 10 to the -6 and they moved it 2 places. So this would be -5, this would be the -4. And so that's how they get 2 times 10 to the -4. Now, this is another one that I'm not a big fan of their answer, because what we said is we're going to try to stick to engineering notation, which allowed us to move within these common units, milli, micro, nano, pico. And so I don't really like the way they've moved it, but in terms of what is the same, 200 microfarads is the same number as B, 2 times 10 to the -4 farads. You can see here's where we started, right? Micro. And what they did, this little example, what they're showing you is if I started here at 200 micro and I moved 1, 2, 3, 4, 5, 6, right? Because that's what micro is. Well, if I move back 1, 2, 3, 4, that's 2 to the 4th. That's the same number. Once again, it's just a matter of those conversions. And you've also in the class, you may have already worked some or all of the movement between milli, micro, nano, pico, and kilo, going the positive direction. You may have worked a lot of those problems, but there's a sheet in there that allows you to fill out the table to move back and forth so that you feel even more comfortable with the conversions. The base unit of charge. If we think about volt, we said was that potential difference. We've already said that the ampere or amps, that's the flow, and ohms is really the resistance. And so this term that we don't use a lot, this coulomb, is what we're talking about in terms of our base unit of charge. It's an amount of charge. It's an amount of electrons, if you will, a certain amount of electrons. And so that's a base unit of charge is the coulomb. The reactance of a capacitor is 0.05 microfarads at a frequency of 1,000 hertz will be. All right, so what they're asking for is our capacitive reactance. And remember, the formula for that was X sub C is equal to 1 over 2 pi FC. The reactance of the capacitor is 0.05 farads at a frequency of 1,000 hertz will be. Let's just take a look at what they're. You can see they've taken our formula for capacitive reactance, which was 1 over 2 pi FC. Remember, F is the value of the frequency. C is the value of the capacitor, and just plug them in. 1,000 hertz, 0.05 microfarads, and do the math. Now, once again, no calculator. You know, they're gonna keep it easy, so you know, it's not likely you'll have to do this calculation. Resistors of 10, 15, and 6 are connected in parallel. The total resistance is, so we have 10 ohms, 15 ohms, and 6 ohms are all in parallel. You know, we can't use our shortcut because they're all different values. We've got multiple values that are below the smallest one, right? And so 6 ohms, we know it's going to be smaller than the smallest. And so in order to properly calculate this answer, it would be, you'd have to use the reciprocal of the sum of reciprocals. So 1 over 10 plus 1 over 15 plus 1 over 6. And so let's look at that calculation, right? I'm telling you to discard the 31 because it's obviously greater than 6. And here's the formula: 1 over 10 plus 1 over 15 plus 1 over 6, which gives us 1 over 0.332 or 3 ohms. Usually what I hear from folks who have taken the test, you're having to calculate parallel. You know, usually it's either they're only giving you one value that is less than the smallest resistor in parallel, so that's a dead giveaway, or they give you typically the same resistors in parallel, which means that you can take that resistance, divide it by the number of resistors to get the equivalent resistance. Two materials commonly used in transistors. D, barium and xenon. Definitely not, right?
Hey.
A, exactly. Germanium and silicon. Those are going to be the two. Now, do you remember what the appropriate voltage is required to forward bias silicon and germanium?
That was my question.
0.7.
0.7 for silicon, and how much for germanium?
0.3.
0.3. Very good. Perfect. A parallel circuit of 4 branches has a 100 ohm resistor in each branch. The total resistance would be C, right? That's the shortcut. That's the one where I've got equal value of resistors, and I just divide it by the number of resistors that I have. And so 100 divided by 4 gives me my answer of C, 25 ohms. Very good. 1 microhenry is
A?
so micro is 10 to the what?
Minus 6.
Minus 6, right? So 1, 2, 3, 4, 5, 6. That looks right. So it looks like A, right? It's just a matter of moving the decimal the right number of places. Once again, it's all about knowing the values, you know, in terms of those really 4 going negative and 4 going positive. If I know those 4 negative and positive, and multiples of 3, you know, -3, -6, -9, -12, 3, 6, 9, 12 in the positive direction, then those become much easier. The ammeter in the circuit shown would read So we've got 12 volts applied and we've got a 64 ohm resistor. Right, so our total resistance is 64 ohms. Our voltage is 12 volts. What's our current going to be?
$12 divided by 64.
Yep, 12 divided by 64.
I don't have a calculator.
This is one of those that, yeah, you won't have a calculator, but you can still longhand it and you could get pretty close. Okay. So there's two steps, right? I mean, you do the math and it comes out with something that is, 0.18, whatever. And then you got to convert that, right? The 0.18 to milliamps. This is another great example. Instead of representing it as 0.18 amps, let's go ahead and do the conversion. Move it 3 places. So this is going to be times 10 to the negative third, which is 187 milliamps. Yes. Very good. Magnetism that remains in a material after the magnetized source has been removed is called a
D.
D. And so the answer is C. Keep in mind, electromagnetism.
Yeah, that's what I said. That's what I said. Yeah.
Yeah, yeah. But you're 100% right, because when we're in terms of, well, 100% right. You're 80% right. In terms of electromagnetism, when we have something that we are magnetizing, as we talked about, which we apply electricity and we get that magnetic field. Yeah, that's electromagnet, and then that residual magnetism is what's left over. Primary cell differs from a secondary cell. So we're talking about batteries here. Primary cell can be recharged. Secondary cell cannot. A secondary cell can be recharged. A primary cell cannot. Primary cell is always a dry cell. Secondary cell is always a wet cell. Secondary cell always has 2 active materials. A primary only has 1.
B.
B, exactly. So when we're talking about that secondary and primary, secondary cell is what we're used to in terms of all the devices that we use, that we charge that battery up, those cell phones and those anything and everything that we have to continually charge and recharge and fight that battle. Primary cells are those that we put a battery in and it's only got such a whatever the life is going to be, and then we replace it. Absolutely. Current passing through a conductor increases. The magnetic flux surrounding the wire will increase, decrease, remain the same, either increase or decrease depending on the applied frequency. What do you think? What are they talking about in terms of that magnetic flux?
I'm going with C.
Going with C. Okay. So it'll increase, right? So it's saying that magnetic field around the wire, if I have a current flowing through that wire, it's going to create that magnetic field. If I increase the current, it's going to increase the magnetic field. One thing to think about in terms of the going back to those meters, those clamp-on meters, if it always remains the same, then those meters would remain, they'd measure the same field, which means they would always give the same current reading. as the current in the wire increases, that clamp on meter that I'm going to actually measure the magnetic field around the wire is going to change based on the amount of current that's flowing in the wire. All right, 3 unequal resistors are connected in parallel across a 120 volt line. An open in any resistor removes the voltage from all. An open in any resistance. What's that?
The first one sounds right.
The first one sounds right?
Yeah.
Okay. An open in any resistor removes the voltage from all. So we've got 3 unequal resistors that are all in parallel. So they've all got 120 volts across them. And so if we have an open in any one resistor, we'd still have voltage applied to the other 2 resistors. Right? B, an open in any resistor causes the current to decrease in the remaining resistors.
D.
120 volts exists on all resistors. D, the currents would divide equally among the resistors. What answer did you say?
D, but I don't think it's D.
D, but I don't think it's D. Okay, so the currents would divide equally among among the resistors. If the resistors were the same, then yeah, we would have the current would be divided equally. But this says that 3 unequal resistors, so it's not going to be D. B, an open in any resistor causes the current to
D.
decrease in the remaining resistors. Which answer did you say?
C. It would still be 120 volts across all of them.
Yeah, it'd still be 120 volts. If we had the voltage is common in parallel, right? I mean, that was one of the early tenets that we said, and so therefore, all of those resistors are still in parallel. We're still going to have 120 volts across those resistors. Absolutely. All right, so we're here at 9:30, 8:30 your time. Let's take a break and come back at a 1:45. All right. See you in a few. Okay, going back to the classroom, just want to point out a couple things. You've got under the general section, you know, these are the practice questions for the TKT that you've had there for the entire course. I'm going to add the other set of questions underneath that. You've also got your series parallel, and series parallel circuit practice problems, step-by-step guides, along with that schematic symbols, right? I got all of the recordings uploaded. And so at the end of every session, you will have your video recording of session 1. You also have videos. Now, when you go to these videos, you know, it's a recap of what we've talked about. These will either be me or one of our other instructors talking about these individual pieces. And so feel free to review those pieces as well. All the quizzes, you still have all the quizzes, and they should be open so you can take those as many times as you want. So just make sure that you go in and you utilize the pieces that are in this course. What I want to do now is stop sharing this. I want to open it up to you guys. We kind of went through a portion of some of those practice questions. We covered flow charts like we were talking about we wanted to do tonight. We did hit relays just because that came up in the schematic session. But I wanted to open it up and see if, what do you guys want to use this last hour for. There is any review that you want to do. If there's a topic that you want to go back and take a look at, anything throughout the entire course, whether it was electronics related, whether it was some of our conversions, some of our logic, some of our different anything and everything. So I open it up to you, and just to see if there's some areas that you guys want to go back and take a look at. So I'd love to think that means that I've been completely clear and covered everything well, but I realize there's probably some folks that have some questions that you just don't want to ask it in the open forum, and I understand that. You feel free to email me as well. Is there anything you guys want to go back and maybe take a look at some of the questions, maybe anything? I don't want to control all the time and not give you guys a chance to ask some questions and make sure you got some clarification. All right, well then let's do this. If you have questions that you don't want to ask to the entire group, if there's something that you'd like to go through, or that feel free to shoot me an email, or what I'll do is anybody have any questions about the makeup of the class and the way the class is laid out? Is everybody anybody confused about any location of any resources? Okay, well then here's what we'll do. I'm going to go ahead and turn the time back to you and let you go in and utilize the course resources as you see fit during this time. But I'm going to hang right here. I'm not going to continue recording. I'm going to cut the recording off, but I'm going to hang right here so that if you guys have any questions, if you want to cover anything, just let me know. Otherwise, I appreciate your attention during the course. You guys have been a fun group to be with the last 6 weeks or so, and I wish you all the best on your TKT. I wish you happy holidays, and I hope things go well for you in the future. You've got my email. Feel free to reach out if there's ever anything that you need from me. Also, once you pass the TKT, when you take it and you pass it, how about send me an email and just let me know so that we can celebrate. We like to share the information that other people have passed, and so let me know when you pass, because I know you will. All right. If you got no questions, then I'm going to turn it back to you, and you guys dive into the class and use this time productively. But I'll be right here. All right. So I'll be here if you have any questions until 10 o'clock your time, 11 o'clock my time.
Thank you, Mike. Hey, just to give you a heads up on it, I took the test months ago, and I know there's a couple of things on there, but that you covered it's pretty much on there, but there are word problems.
Okay.
On there. So just to give you a heads up, if everything that you've been showing us is on there, but also there's word problems. Like one example was a computer company in the Southwest sold 23% of chips. Northwest sold 16%. I think Southwest sold 82%. What is the total revenue they made? Something like that. They had a couple of word problems on there like that.
Okay.
So just to let the guys know on here that there's going to be a couple of questions on there as well.
That's great. And the thing with those word problems, you can get lost in the words. The easiest thing for me to do is take that word problem and write down the data, right? They give you so much information that your head begins to spin. Just write down the data that you need and then do the calculation that way. try to simplify the word problem as opposed to, getting lost in all the words. Yeah, thank you for that information. That's great information to have. You guys can, you've been doing a lot of this math. You've been, working through some of these quizzes. You can do those word problems. It's just a matter of having the confidence to take the information down and move forward. Also, use good test taking skills. It's multiple choice, and so therefore, it's okay to utilize the answers they give you to work backwards sometimes. If you are unsure, we'll take a look at, are there two answers that are obvious, not even in the ballpark, and then there may be two that are close. Just use some of those good test taking skills so that you can eliminate the wrong answers and improve your chances of getting the right answer. But yeah, thank you very much for sharing that information. That's good to hear that, you heard a lot of the same thing that you saw in the test, but, word problems are, they do trip people up. So just be careful with those and attack those with confidence and write down the data that you need to make the calculation. Simplify it is what I'm getting at. All right, so I'm going to turn the time back to you guys. I hope you have, like I said, a wonderful holidays and stay in touch. All right, I'll be here until top of the hour if you have any questions.
Thank you, Mike. We really
Thank
appreciate
you.
it.
Hey, I really
thank you,
appreciate
Mr.
you
Mike.
guys. Yeah, thank you.
Hey, Mr. Mike, I have a question.
Absolutely.
I just want to know, do they reach out to us when it's time to take the test, or how does that go?
So my understanding is you have to register for the test, and that may be different depending on where you're located. But I would say that you need to take action and sign up for the test, and don't wait on them to reach out to you. I'm not sure who in your situation would be the direct contact to sign up for the test, but I would say.
I believe. I'm sorry. I believe
Go ahead.
there has to be a job posting for you to be able to take the test.
Oh, is that right?
Yes, that's correct.
Okay. Okay. Very good.
Your best option is to just apply for every job. And then once you get to take the test, since it's fresh on your mind, and then just deny the job, even if it's somewhere way out, away from you or whatever, just try to apply for it.
Cool deal. Thanks, man.
That sounds like good advice. Yeah, you want to take that test as soon as you can. So whatever measures you need to, whatever actions you need to take, I'd go ahead and do it.
I appreciate it, y'all.
All right, y'all have a good one.
Thank you.
Thank you.
Recording stopped.
Mike, you said we're gonna have
What's that?
we're gonna have access for about a year. You said.
Yes, you should have access for a year. If something happens, and I had some students that got kicked out, they took class about 6 months ago. Yeah, if you'll shoot me an email, I will make sure that, if you've been kicked out for some reason, that you get back in.
Okay, and it's gonna be the same email you emailed us from within the class.
Yeah. If you send me the email, Mike.Hogan704, I'll get that.
Okay, sounds
All right.
good. Thank you.
Thank you.